Imagine a ghost in the universe. It's a place where the rules of space and time as we know them break down completely. This isn't science fiction. This is a black hole. It's a region of space-time where gravity is so incredibly strong that nothing, not even light, can escape. Think about that for a second. Light is the fastest thing in the cosmos, zipping through space at nearly 300,000 kilometers per second. Yet, even this cosmic speedster is trapped by the immense gravitational pull of a black hole. It's like a waterfall with no bottom, a one-way cosmic street leading to an unknown destination. Scientists are fascinated by them because they represent the most extreme conditions in the universe, a laboratory for physics we can only dream of. So, what makes these objects so mysterious and powerful? It all comes down to gravity. Albert Einstein, in his theory of general relativity, taught us that massive objects warp or bend the fabric of space-time. You can picture it like placing a heavy bowling ball on a stretched-out rubber sheet. The ball creates a dip in the sheet. Now imagine an object so incredibly dense, so much mass packed into such a tiny space that the dip it creates is infinitely deep. That's a black hole. Black holes are not born quietly. They are born from the spectacular death of the universe's biggest stars. Imagine a star many, many times more massive than our own sun. For millions of years, this star shines brightly, a giant nuclear furnace, fusing hydrogen into helium and other heavier elements in its core. This fusion process creates a tremendous outward pressure, a constant explosion that pushes against the star's own immense gravity. It's a cosmic balancing act. For most of the star's life, that push and pull are in perfect equilibrium, keeping the star stable. But this balance cannot last forever. Eventually, the massive star runs out of fuel. The nuclear fusion in its core begins to sputter and die. With the outward pressure gone, gravity wins the battle. In a fraction of a second, the star's core collapses under its own colossal weight. The collapse is so violent it triggers a cataclysmic supernova. The outer layers are blasted into space in a brilliant display that can outshine a galaxy. This explosion seeds the cosmos with heavy elements like iron, gold, uranium, the very stuff that makes up planets like Earth, and even us. But what happens to the core? For the most massive stars, the collapse doesn't stop. It squeezes that matter into an infinitely small, infinitely dense point. This is the moment a stellar mass black hole is born. All the mass of a star is now concentrated into a space smaller than an atom. This creates the extreme gravitational field we talked about. Every black hole is surrounded by an invisible boundary, a line of no return. This boundary is called the event horizon. It's not a physical surface you could touch like the ground, it's a point in space. On one side of this line, escape is still possible if you have a powerful enough rocket. But once you cross it, there is no turning back. Gravity becomes overwhelmingly powerful. You would need to travel faster than light to escape, and Einstein showed us that is impossible. Imagine you are an astronaut in a spaceship bravely approaching a black hole. You watch your fellow astronaut, Jane, float towards the event horizon. From your perspective, a very strange thing happens. As Jane gets closer and closer to the edge, she seems to slow down. Her movements grow sluggish. The light signals from her suit take longer and longer to reach you, becoming redder, becoming dimmer. This is due to a phenomenon called gravitational time dilation. To you, Jane would appear to freeze in time right at the edge of the event horizon. But for her, everything is completely normal. She checks her watch and time ticks as usual. So what awaits Jane, our brave astronaut, after she crosses the event horizon? Where does this one-way journey lead? According to our current understanding of physics, all paths inside a black hole lead to one place, the center. And at the center lies something so strange, so bizarre, that our science has no words to truly describe it. We call it the singularity. It is the heart of the black hole, the point where all the mass that has fallen into it is crushed into an infinitely small, infinitely dense point. It is a place where space and time cease to exist as we know them. Imagine taking Mount Everest and squishing it down to the size of a grain of sand, and then squishing it even more, forever. That gives you a tiny glimpse into the idea of a singularity. Here, the density and gravity are infinite. The laws of physics that we use to describe the universe, Einstein's theory of general relativity for gravity and quantum mechanics for the world of tiny particles, break down completely. They give us nonsensical answers like dividing by zero. The singularity represents a hole not just in space-time, but in our very understanding of the universe. What happens to space and time at the singularity? Our theories suggest something truly strange. As you approach the singularity, the fabric of space-time becomes so warped and curved that space and time essentially swap roles. What was once the forward direction in time becomes a direction in space, pointing directly towards the singularity. It is the end of time itself. Of course, this is all theoretical. No one has ever seen a singularity, and no one ever could and survived to tell the tale. Long before our astronaut Jane reaches the mysterious singularity, she would face a much more definitive and honestly gruesome fate. This process actually has a surprisingly playful name: spaghettification. It's the ultimate consequence of the extreme gravity near a black hole. So, gravity, as you may know, gets weaker with distance. This means that if you're falling towards a black hole, the part of your body that's closer to it will be pulled much more strongly than the part that's farther away. This difference in gravitational force is known as a tidal force. Let's imagine Jane is falling feet first towards the black hole. The gravitational pull on her feet will be immensely stronger than the pull on her head. At first, she might just feel like a gentle stretching sensation. But as she gets closer, this stretching force would grow exponentially. Her body would be pulled apart, stretched longer and longer, and at the same time squeezed thinner and thinner from the sides. It's kind of like a piece of spaghetti being pulled from both ends. Her body would be drawn out into a long, thin stream of individual atoms. And well, this is really not a quick or pleasant process. This stretching happens to everything that falls into a black hole, not just astronauts, stars, planets, clouds of gas. As this matter is ripped to shreds, it forms a swirling, superheated disk around the black hole called an accretion disk. Black holes are no longer just a theoretical concept. We have found them. We've studied them. We've even taken a picture of one. One of the most famous black holes is Sagittarius A star, the supermassive black hole at the heart of our Milky Way. It's about 26,000 light-years away, in the direction of the Sagittarius constellation. For decades, astronomers tracked stars orbiting the galactic center. They saw stars whipping around an invisible point at incredible speeds. Some reached several thousand kilometers per second. There was only one object that fit the data: a black hole about 4 million suns. The Event Horizon Telescope gave us our first direct look at one of these giants. In 2019, they released the first ever image of a black hole. It wasn't Sagittarius A star. It was a much larger one at the center of Messier 87, M87, M87. This behemoth is 6.5 billion times the mass of our sun. The image isn't the black hole itself, it traps light. Instead, we see the black hole's shadow, a dark central region surrounded by a bright, fiery ring from the accretion disk. That image was a monumental achievement, confirming Einstein's theories. Another famous system is Cygnus X1, discovered in 1964, one of the first widely accepted black holes. It's a stellar mass black hole, about 21 times the sun. It's part of a binary system. Its companion is a massive blue supergiant, and the black hole pulls material from the companion, forming an accretion disk that emits powerful X-rays. These discoveries come from many telescopes and observatories: Chandra, Hubble, ground-based arrays in Chile and Hawaii. They measure stellar motions, detect radiation from accretion disks, and now even listen for gravitational waves, ripples in space-time from colliding black holes. Each new observation adds a clue, turning speculation into observational science. We are living in a golden age of black hole discovery. So, is a black hole truly a one-way street? Is anything that falls in lost forever? The great physicist Stephen Hawking came up with a revolutionary idea that suggests otherwise. In the 1970s, he combined the laws of general relativity with quantum mechanics and discovered something amazing. He predicted that black holes are not completely black. They should slowly leak a tiny amount of energy, a faint glow of particles, over very, very long periods of time. This phenomenon is now called Hawking radiation. It's a very slow process, but it means that black holes can, in fact, evaporate. According to quantum physics, empty space is not truly empty. It's a bubbling, fizzing soup of virtual particles that pop into existence in pairs, a particle and its antiparticle, and then almost instantly annihilate each other. But if one of these pairs appears right at the edge of a black hole's event horizon, it's possible for one particle to fall in while the other escapes. The escaping particle becomes a real particle and flies off into space. To an outside observer, it looks like the black hole has just emitted a particle. Because of the laws of energy conservation, the black hole must lose a tiny bit of its own mass in the process. This evaporation process is incredibly slow. For a black hole the mass of our sun, It would take longer than the current age of the universe for it to evaporate completely. For supermassive black holes, the timescale is almost unimaginable, but it does mean that black holes have a finite lifetime. This also leads to a deep puzzle called the information paradox. If a black hole evaporates, what happens to the information about all the things that fell into it? The laws of physics say that information can never be destroyed. So where does it go? This is one of the biggest unsolved problems in theoretical physics today. Another fascinating, though highly speculative idea is the concept of a wormhole, an Einstein-Rosen bridge. Some solutions suggest a black hole might be one end of a tunnel through space-time, a bridge connecting two different points in the universe, or even another universe entirely. However, most physicists believe that such tunnels would be incredibly unstable and would collapse the instant anything tried to pass through them. Despite all our incredible discoveries, the list of what we don't know about black holes is still incredibly long. Perhaps the biggest question of all is, what truly happens at the singularity? Our two best theories fail us here: general relativity and quantum mechanics. We need a new theory, a quantum theory of gravity. Scientists are working on candidates like string theory, loop quantum gravity. What replaces the singularity? Is it a quantum fuzzball or something else entirely? The singularity could be replaced by exotic structure. We simply don't have the science yet. Another huge mystery is the information paradox. When something falls in, the information that makes it unique, its shape, its chemical composition, its temperature, seems lost behind the event horizon. But quantum physics says information cannot be destroyed. When a black hole evaporates via Hawking radiation, where does the information go? Does it leak out with the radiation, subtly scrambled? Is it stored on the event horizon like a cosmic hologram? Or is it transferred to another universe? Solving this paradox is key to quantum gravity. We also have questions about the black holes we see. How did supermassive black holes grow so big so fast in the early universe? Did they form from collapsing primordial gas clouds? Or did they grow from smaller seed black holes by mergers and accretion? What about intermediate mass black holes? Those between 100 and 100,000 suns. They should be out there, but they are incredibly hard to find. Some physicists seriously consider that a new universe could be born from a black hole singularity. This idea, fecund universes, casts black holes as seeds for new cosmoses. These questions push the limits of science and philosophy. They remain deep, tantalizing mysteries waiting to be solved. So, after our cosmic journey to the edge of reality and back, we are left with the ultimate question. Will we ever truly know what's inside a black hole? The honest answer is, maybe not. The very nature of the event horizon makes it a perfect cosmic prison. It prevents any information from the inside from ever reaching us on the outside. We can't send a probe in and have it report back. Any astronaut would be on a one-way trip, but humanity is curious and persistent. Future telescopes, gravitational wave observatories, and new theories may reveal more. Perhaps the greatest discoveries will come from equations and imagination as much as from observation. The universe is waiting. Thanks for watching. If you loved this journey, subscribe for more explorations of the cosmos.